is so that we can discuss or understand what our coefficient of determination is, so our r squared, okay? So there is another numerical quantity that tells us how well the least squares line predicts values of the response variable y, okay? And that would be r squared. So the standard deviation of the residuals gives us a numerical estimate of the average size of our prediction errors, okay? There is another numerical quantity that tells us how well the least squares regression line predicts values of the response y. It is equal to the square of r, but much more is to that story, okay? So it's not just that you square r, it means a lot more to us, okay? So r squared is referred to as the coefficient of determination, okay? It's the fraction or the proportion of the variation in values of y that is accounted for by the least squares regression line, okay? They tell you how to calculate it, and again, not something that we calculate by hand, okay? So r squared tells us how much better the least squares regression line does at predicting values of y than simply guessing the mean y for each value in the data set. Okay, consider if we needed to predict a backpack weight. So if you remember that backpack problem with the hikers in chapter 6, okay, if we needed to predict a backpack weight for a new hiker, but we didn't know each hiker's weight, what we would do is we would use the average backpack weight of the data that we actually had as our prediction, okay? The horizontal line here is at the prediction at the mean of the backpack weight. Okay, so if we use the mean backpack weight as our prediction, the sum of the squared residuals would be 83.87. Okay, if we use the least squares regression line to make our prediction, the sum of the squared residuals is 30.90. Therefore, 36.8% of the variation in backpack weight is unaccounted for by the least squares regression line. And here comes r squared. Okay, r squared is going to be 63.2%. And what that is it's the variation in backpack weight that is accounted for by the linear model relating backpack weight to body weight. Okay, so really we just need to know what these numbers are and kind of what we can do with them. So we're going to run through this quick example, and that's really all you're expected. You're not expected to calculate these things. You'll always just, you'll have them or you'll be told them, okay? So this is actually going back to the SEC football question in Chapter 6 that we were analyzing, okay? You don't need it necessarily in your calculator still. I just give you these values, so don't worry about that. Okay, so we have been looking at the relationship between the average number of points scored per game and the number of wins, which is our y, for the 12 college football teams in the SEC. A scatter plot with the least squares regression line and a residual plot are shown. The equation of the line is follows. Also, I give you S and R squared. The first thing I want to do is calculate and interpret the residual for South Carolina, which scored 30.1 points per game. Okay. So the predicted amount of wins for South Carolina is, I need a hat on that, white hat, is as follows. So it's going to give you 9.4 wins. Okay, I used my equation up here. Okay, from that, I know that my actual was 11. Okay, so I'm going to take my actual and subtract my predicted, and so my residual here, 1.6 wins. So in terms of interpreting that, we would want to say that South Carolina won 1.6 more games than expected based on the number of points they scored per game. Okay, so is a linear model appropriate for these data? So now I'm just going to look at that residual plot there, okay? There's no obvious leftover patterns in the leftovers in your residual plot, okay? This would be understood as completely random scatter, okay? And because it's completely random scatter, yeah, an appropriate, a linear model is definitely appropriate here. Okay. Now for interpreting S, which was our standard deviation of our residuals. Okay. So when using the LSRL, okay, with X being the points per game and Y being the number of wins, and it's the same as we always interpret standard deviations, we will typically be off by about 1.24 wins. And now for how we interpret R squared, okay? Your R squared value was 0.88. So about 88% of the variation in wins is accounted for by the linear model relating wins to points per game. Okay, we're going to put a lot of these interpretations, how to interpret these in our flashcards that we'll create and our notes. I would write them down, but we'll reflect more on them in class, and that's the end of this video.